Okay, so today we'll be looking at electric charges. An electric charge is a property of a particle that causes it to experience a force when it's placed in an electromagnetic field. And we have two types of charges, the positive charge and the negative charge. We can generate this positive charge by rubbing a glass rod with silk, and we can generate the negative charge by rubbing an ebonite rod with four. I'm sure we still remember that like charges repel each other and unlike charges attract each other. Alright, so what is static electricity? This is the kind of electricity that doesn't require electron flow. Okay, there's no change in potential between 2 points that generates current. Okay, so this happens just because of an imbalance between the positive and negative charges. Alright, if we remember, an atom has positive charges, has negative charges, and these charges are balanced for the atom to be neutral. Okay, so once there is an imbalance of these charges, we have an ion, okay, or a charged atom. Of course, we remember that substances can be classified into two groups, conductors and insulators. All right, and we all know the criteria behind these classifications. Okay, conductors have very low resistance to electricity and to heat, while insulators have a high resistance to the flow of electrons, that's to current, and to, of course, heat. Alright, so that being said, how do we produce charges? There are three basic ways charges are produced. Okay, the first one is by friction, the second one by contact, the third one is by induction. Okay, so by friction, this is you transferring electrons from one material to another by rubbing each of them against themselves. Okay, so once there's that transfer, you create that imbalance. Right, so the substance that has lost electrons becomes positively charged, while the one that has gained the electron becomes negatively charged. Okay, because electrons are actually negatively charged, and we know protons are positively charged, but protons don't easily leave an atom. So what actually leaves an atom is usually the electron. So if an electron is moved from one substance or from one object to another, then the object that lost the electron becomes positively charged, while the one that gained it becomes negatively charged, because the one that gained it will have an excess of electrons, so which makes the excess of the negative charge. Okay, and the one who lost is going to have an excess of positive charge because it has lost an electron and lost a certain magnitude of negative charge. An example of this kind of situation is when you rub a comb on your hair, or you rub an ebonite rod on four. Of course, I'm sure we've all experienced rubbing our comb on our hair and then trying to use it to pick a piece of paper, and you see that the comb attracts the paper. Okay, or a ruler, plastic ruler, you rub it on your hair and then you try to pick a piece of paper. You see the ruler attracts that piece of paper. Okay, so the rubbing of the ruler or the pen or whatever it is on your hair, okay, creates a transfer of electrons, and by that you have a charged ruler or a charged comb or whatever it is, and so once you take it close to the paper, it attracts it. So the second classification we have is by contact, and this is basically by conduction. This is when uncharged bodies can become charged just by bringing charged objects close to them. Okay, you don't make them make contact with these other objects. They just come close to these objects and these objects become charged. Okay, so pictures here show an example. So this is like the first stage. We have object 1, object 2. You see this one is negatively charged and this one is neutral. It has positive and negative charges equal. Okay, it's a neutral body. All right, all of a sudden we bring this object close enough to this one, and so what happens is you have this object which is negatively charged attracting the positive charges towards itself, and then the negative charges are left behind. All right, they are pushed to the back. Okay, so if we then connect the back side of this object to ground, we'll lose these negative charges to the earth, and then these objects will then become positively charged once we remove our rod, okay, that we've connected to the ground. Automatically it becomes positively charged. So you can see that we have automatically charged this body by induction without it making contact with the charged objects from the stage 1. So let's talk about the gold leaf electroscope. It's an instrument used for detecting and testing of small electrical charges. Its essential features are, of course, we have the brass disc, we have the insulator. This insulator is something placed here, which of course is in contact with this rod, alright? But of course, it can't exchange charges with this rod because it's a poor conductor. Of course, that's the brass rod I just talked about. We have the gold leaf, okay, and then we have a metal case that is earthed. Alright, so the metal case is earthed to prevent accumulation of charges from external sources. Then the position of the leaf shows the presence of charge in the rod, and the electroscope can be charged by contact or by electromagnetic induction. Okay, so these are the basic things we need to know about the electroscope. Alright, so we can charge by contact, by electromagnetic induction. There's no point charging by friction. So there are two uses of the gold leaf electroscope. The first one is to detect good or poor conductors. You can use it to detect what is a good conductor or what is a bad conductor, and you can use it to determine the magnitude and the type of charge a body has. Okay, so let's run through how this can be done. Okay, so we're assuming our electroscope is charged and our gold leaf is open, is not collapsed yet, is open. Alright, now if you bring an object and put it in contact with the brass disc, okay, if there's a rapid collapse of this leaf back to this position, then it means what we have is a good conductor, because it has just conducted the charge of this electroscope out. Okay, so this leaf collapses, it means we have a good conductor. Now if we have a gradual and slow collapse, it means that body in contact is a bad conductor. So the speed of collapse, the rate of collapse will make us understand how good a conductor we brought in contact with the brass disc. Okay, that's how we detect a good or poor conductor. So let's move on. Now if we have to detect what type and magnitude of charge a body has, okay, we have to first charge our electroscope. So we have to know what charge it has, whether the negative or the positive charge. So if we have it charged with a negative charge, all right, and a negative charge is brought to the cap, there is going to be an increase in divergence. Okay, so of course we have our gold leaf in this direction. Okay, we have it here. That's when we charge it with negative charge, we have it like this. Okay, we have this divergence away from its original position. Now if you bring a negative charge to it, this divergence will increase. More like we might now have it in this direction. All right, so this increase in divergence makes us know, oh, we have a negative charge. All right, so now if it's a positive charge, we're going to have our divergence decrease. So you're going to have this happen. Okay, it's going to decrease because you have just brought opposite charges, and of course we remember that opposite charges attract. Okay, so you're going to have this divergence close. Now if the electroscope is positively charged originally and you bring a positive charge to it, definitely we're going to have divergence increase again. All right, because of course in that situation we're dealing with similar charges, so we're going to have an increase in divergence. Okay, like we have here with this black line, there's going to be an increase from this blue position to the somewhere above it, so anywhere from here where the black line is. Okay, we'll have that increase in divergence. While if we bring a negative charge and put it in contact with a positively charged electroscope, we're going to have our divergence decrease. Okay, also if it's an uncharged body, so whether the electroscope is positively charged or negatively charged, if you bring an uncharged body to it, it will definitely decrease the divergence of the gold leaf. So that's basically how we can determine what type and magnitude of charge the body we are bringing in contact with the electroscope has. Charges are usually concentrated at places where the surface is sharply curved. The charge density is highest at these points. So I tried to get these diagrams to show these. So if you look here, we'll see we have, if these red dashed lines are charges, we'll see we have an equal concentration all around this circle. There's an even concentration of charges around it. But when you come to a shape like this, you see we have lesser concentration on this side, and we have more concentration on towards the edge of the shape. This is the reality of how charges concentrate themselves. Okay, so that brings us to the term action at a point. Okay, action at a point is the emission of electrons from sharp points. So you see, because there's a concentration of electrons at this point, electrons can easily be emitted from them because the concentration there is high. Okay, so due to that accumulation of charges, and this is the concept that is used for protecting buildings from lightnings. All right, where you have your lightning protector, this is the concept used, because those charges that accumulate at the tip of your spike on the building has the ability to be easily emitted and repel certain clouds, and that process keeping the building safe.